Good. So this was a postscriptum for last time. And today, the big topic for today will be statistical decision theory. So what is the best classifier that we can hope for and how good is it? And we will discuss this in the context of classification. So far we talked about regression. Now we turn to classification. So I start with some terminology. So I'm using a subheader here, which I call classification, where I introduce some terminology. Yeah. So what we always have is we are given some training set. Just discussed the collection of features and labels. So depending on the field, these can be called features, or these can be called explanatory variables, or these can be called the independent variables. And then we have the labels, or the targets, or we have in a regression context, we would call these the dependent variables. All right, so we have this training set, and what we want are accurate predictions of y given x. And now these labels, they can be of different nature. Yeah, we were discussing in the beginning of the term the different scales that exist, and I mentioned that there is the nominal scale. So this could be nominal, where we talk about a set membership, or this could be ordinal, or it could be defined on the interval scale. And if the outcome is defined on the interval scale, then we call the problem regression. Can be linear regression, can be a multilayer perceptron, can be whatever. If the output is defined on the nominal scale, then we talk about a classification problem. Yeah, and so on nominal scale, if you are into astronomy, you know, you might classify an observation into whatever, you know, scale, quasars versus supernovae versus, you know, whatever you observe. Or if you are into accelerator physics, these can be the different kind of particles. So whenever we try and predict a class, given some input, then this problem would be called classification. And then there is a distinction between parametric and non-parametric methods. In parametric methods, the number of parameters does not directly depend on the size of our training set. Number of parameters in the method does not grow with the number of observations, which we've typically called n here. So if we take linear regression, or if we take a neural network, once we have decided on the architecture, then the number of parameters in this architecture will not grow if we get twice as many training samples. And then, confusingly, there are the non-parametric methods. Where they're called non-parametric, but actually the number of parameters grows with n. Yeah, so they should really be called extra parametric or super parametric or something, but they're called non-parametric, even though number of parameters grows with the number of observations. And an example, we've seen one example, namely a kernel density estimation. The more observations we have, we put the kernel on every single observation, and so the implicit number of parameters grows with the number of observations. Okay. So much for terminology, and we are heading for statistical decision theory, but for this we need Bayes' theorem. I'm sure you've seen it all, so this will be mostly a reminder. So we assume that we have some sample space when we were discussing what is the nature of a random variable, we were talking about this sample space, which is often called omega. And in this sample space, we might have different events. So maybe this here is an so an event is a set of outcomes. I'm calling this one here beta, and I'm having a different event or different set of outcomes which I'm calling alpha. And then we can condition on these things. Yeah? So we can ask if I know that I am in, okay, and here I assume that the size of these events, the area of these events represents their probability. And so if I can ask, the typical question I could ask is, what is the probability of alpha if I know that beta holds? Yeah, so I am now half closing my eyes because I still need to hit beta somewhere, but okay, okay, I managed to hit inside beta, but I was not looking where. Yeah, so I'm conditioning on this event beta, and I'm asking what's the probability of being inside the event alpha or not inside the event alpha. And the way I drew it here is 50-50. Yeah, so but how I can, so here I argued graphically that in this particular case here, in this example, this would be 1/2. And I can relate this to the joint probability. So I can ask, okay, this is getting small for people in the rear, I'm sorry. So the red thing here would be the probability for alpha and beta. So logical conjunction, or I could just say P of alpha comma beta, it's the same thing. And what I can do is divide this probability of alpha and beta divided by the probability of beta. And if I have drawn this well, so maybe the probability of beta here, I claim that this is maybe, you know, a 50th of the whole area. I did not measure it, yeah, but let me claim that beta is around 1/50th of omega. So in the denominator, I would have 1/50th. And then the joint probability is half that. So this would be 100. And yeah, this works out to be 1/2. Okay, and what I used in my, so what we can always write is, if we now have an expectation with respect to random variables alpha and beta, we can write this as expectation of alpha given beta of the expectation with respect to beta. I can even write equality here, not corresponds. And earlier in my correction, it was a special case because alpha was independent of beta, so I could just take the expectation of with respect to alpha and with respect to beta, and then the two factorized. Okay, but this equation here is the basis of Bayes' theorem here. So we can write that this probability of alpha given beta is so using okay, I think we need something else. I also need to say that this okay, so from this equality here, what I get is that the probability of alpha and beta is probability of alpha given beta times the probability of beta. Yeah, so I just multiplied with beta. But I can also do the whole construction the other way around, and then I get the probability of beta given alpha times p of alpha. And now I solve with respect to this term here. Yeah, so I divide by p of beta, and this is what I find. Yeah, and this is the celebrated Bayes' theorem. And because it is so important, each of the terms in there has a name of its own. This would be the prior probability of some event. We have a likelihood. We have an evidence. And we have a posterior. And connecting this with classification, we could write it with alphas and betas, but normally we write it with X for features and Y for labels. So in classification, we would say that the posterior probability of some class given some observation. Would be a product, the likelihood of observing X given Y times, this would be the prior probability of a given class. Divided by P of X, or this I can write also, yeah. If I have several classes, I can write this as a sum over terms that look like the numerator, but for the different classes. So write this here with some y tilde of the probability of X given y tilde times P of y tilde. Yeah, because this will be the joint distribution of X and y tilde, and then I marginalized out y tilde, integrate out y tilde and get the marginal distribution of P of X. Okay, so that would be in classification. And then we have methods that predict the right-hand side. These are called generative classifiers. They estimate these terms on the right-hand side. And there are also methods to directly try and predict P of y given X. These are also called discriminative classifiers. Which estimate directly the left-hand side. Okay, let's look at a few pictures, which I could not draw as nicely on the board. Yes? What the names are. Likelihood prior, evidence, and posterior. Oh, below, class label, prior probability. Okay, thanks for asking. All right, do we have a beamer? Ah. All right, so this is too fancy. I just want this part here. All right. Okay, so here's an example. And again, for those who were not here in the first hour, here, these pictures I put in this document, which you see here. All right. Peter, my screen on this computer, it blacks out regularly. Do you see that all right there? Because on the Beamer, it continues working. No blackouts on your side, okay. Good. Okay, so here's an example. We have a one-dimensional feature space. And in this one-dimensional feature space, we have a probability distribution of X given, let's call this class Y1. And then we have a probability of X given class Y2. And now we can, the prior probability we can obtain by integrating the one or the other. Yeah? So we can ask what is the integrated probability of that. The integrated probability would just be altogether would be P of Y2. I'm sorry. And the integrated probability of the blue curve would be P of Y1. All right, so we have P of Y2. Similarly, if we integrate the blue curve, we get P of Y1. And now we can, from this, compute the posterior. So that's in this, shown here in green, is the probability of this class Y1, the posterior of class Y1 given some location X. No, this is wrong. This is Y2, not Y1. So what we see is that, so I've chosen parametric models here for the blue curve and for the orange curve. I've put them into Bayes' theorem. And what we see is that there is some, okay, let me get a threshold line also at 0.5. Okay, this is meant to be a horizontal line. And it's meant to be at 0.5, okay, more or less. What we see are a few features here, yeah? So here we have a point, wrong. It's not this point that I'm looking for, but here. Here we have a point where on the right-hand side, the orange curve has a higher probability than the blue curve. And this is exactly the location where the posterior probability goes through this threshold of 1/2. Yeah, so on the right-hand side, I have a larger posterior probability for class 2 than for class 1. I also have a crossing point here, and well, here on the left-hand side, both probabilities are really, really small, but still the orange probability, the class 2, is larger than the blue, than the probability of class 1 given by the blue curve. And this is why we have here another crossing with this threshold of 1/2. Okay, so altogether, what this means is that here on the right-hand side, so here on this side, the orange class dominates, and on this side, the orange class dominates, well, and in between, the other one does. And we could draw the complementary probability of the posterior of class 1 given x. We know that the two sum up to 1, yeah? So we must have 0 crossings here and there. It must be approximately 0 here. It must be approximately 0 there. And it will go to roughly 0. It will go roughly up here. So approximately like so. What I've shown here in this turquoise color is approximately what this probability of class y1 given x would look like. Yeah, and P of here, the probability of y1 given x plus the probability of y2 given x, these two posteriors, they will sum up to 1. All right, so much for a concrete example, and I have a few questions for you. Let me type them out. So, question. If you had to predict either y1 or class y2 for some location x, which one would you predict? Second question, when would you rather not make a prediction? So for which x? And third question, here in this above example, we assumed I somehow had knowledge of these probability densities for the different classes. I just invented them, and I knew their exact mathematical form, and I could put them in the equation. I just played Oracle. Yeah, I just pretended that I knew. But in real life, we are not given these curves. We are only given observations. Yeah? So let's say from the orange class, we are only, my pen refuses to work. From the orange class, we're only given samples. Okay, I'm multiplexing now. Okay, not a good idea. So we're only given samples from the orange class. We're only given samples from the blue class. We're not given these nice bell-shaped curves. So if we're only given samples, how would you estimate the relative or the respective quantities? Yeah? If you have access to samples only, to samples from the probability distributions of both classes, how would you estimate the quantities that we need for this kind of plot or to make this kind of prediction. Okay, good. Those are my questions for you, and we have, take 5 minutes, please, to think about them a little, and then we discuss what are your insights. Hallo Mats. All right. Let's see what you have found. So, first question. First question is, so we have somehow these curves available, and I ask to make a prediction for either class, let's say right at this location. Yeah. So, which class would I predict and why? Yes. We would predict the blue class, the class 1, rather than the orange class, the class 2, with and the posterior probability would be 0.7 something, yeah. And yes, I agree. And why would we vote for the blue class rather than for the orange one? Yeah. Okay. So you said that it has a larger posterior probability, and hence we predict this one. Yes, that's completely reasonable. And an assumption that we've made implicitly here is that wrong predictions in each direction are equally bad. In real life, this is often not the case. Yeah? In real life, making an error of one kind is much worse than making an error of a different kind. Yeah? So, and that's a very, very difficult trade-off in real life. So in physics and also in non-physics applications. So if you think, for example, you have to construct an emergency braking system for a car. Your car has cameras. You don't want to run over pedestrians, or let's say a kid in particular. And if the classifier wrongly decides that no, this was not a kid, but in fact it was, that's really terrible. On the other hand, you can say, okay, I tune my classifier to always be on the safe side. And then, out of the blue, your car might make these emergency brakings, and the person behind, might bump into you, even though there was, nobody. That also makes for not so happy drivers. So these are very, very difficult trade-offs. But in particular, this trade-off of how bad is the error of one kind versus the error of the other kind, that's not something the machine learning algorithm can tell you. Yeah? The machine learning algorithm can only tell you, okay, I estimate these probabilities, but what you make of these, that's a design choice. Yeah? That you need to specify, you the designer. Okay, good. This was for question 1. Question 2 was so this axis here is the x-axis. Where would you rather not make a prediction for either class? Yeah. So around the crossing points where the two posterior probabilities are too similar, you would rather not make a prediction, but you would say, I'm just unsure. Yeah, makes sense. And any other suggestions? Yes?
I would also not make any prediction at the far edges of the probability distribution, because there the probability for each class is quite low, and the only thing why the class y2 is higher than y1 is just because of the difference they have.
Yeah, it's actually, this class is also a bit broader. And okay, so the statement was, And I agree completely that you would rather not make a prediction. So, you know, if we just look at the posterior, then we can say, but look, here, the posterior probability for class 2, it's really, really high. I'm really, really sure of my prediction. But if you look at the probabilities for both classes, they're approximately 0. Yeah, so in my formula, I have a numerator which is very nearly 0, and I have a denominator which is very nearly 0. And you know, that doesn't sound too good, right? If you divide by, you know, two things which are nearly 0 by each other. So if we now, and that links to the third question, if we have to estimate these things from a finite sample set, I would not be so confident that we get this part here right. And you were saying something else. You were saying okay, I'm not sure I'm reproducing this right. But so why does the orange class win here on the left-hand side? I mean, its center of mass is more to the right, and yet the orange class wins. In this particular case, both were Gaussian distributions, and the orange one has a bigger standard deviation, and hence it both decay exponentially, but the orange one decays a little bit slower. Yeah, and this is why the orange class out here, the far left, wins again. Okay, and these two questions, they link directly to what we'll discuss after the break. But the third one, if you have access to samples only, how would you estimate the quantities involved? Yes? So I think what you suggest is having a histogram type approach where I count in each bin how many samples of a particular class. Yes, that works. Any other suggestions? So by what you suggest, you would have a histogram, and then for each bin, yeah, you could make a decision, and you could even get an uncertainty estimate and so on. Yes. Other suggestions? Yes. Yeah. So you suggest using a parametric model for each of the two classes. For example, so you said the mean and the moments. If we say Gaussian, then we only need the mean and the standard deviation. But if we use higher moments, then we can have more flexible parametric estimates. Yeah. For example, if the distribution is skewed, then we know Gaussian will not be good. Yeah, very good. Yes. Yeah. Yeah. So what he said was it depends on the number of samples. It also depends on the number of dimensions. So in high dimensions, with the histogram, you're going to be lost. Yeah, because either you make your bins small, and then most bins will be empty, or you make your bins very large, but then you lose the fine structure. Yeah, so the parametric model that you proposed will work much better in high dimensions, or if we have relatively few samples. Yeah. More suggestions? Yes? Could do kernel density estimation for each of the two classes. Very good, yes.
Consider an interval around it and recover the proportion of parameters that fit it, maybe with some confidence.
Yeah, so I think what you suggest maybe would be called the epsilon nearest neighbor estimate. So we put an epsilon ball around each observation, and we count how many are in there, and we can do nice Bayesian statistics and so on. That's good. The only thing is, if we define this epsilon ball, it is somehow like using a density estimate with a 0, 1, so a function which is constant inside and 0 outside, and that's a bit rough as points enter the ball or not. Yeah? But we can, as you say, we can do nice statistics about what are our uncertainties in the estimates. Okay, cool. So you've really, really covered a lot of ground. These two questions relate directly to what we'll discuss after the break. And the third question, really summarizes half of what's going on this semester. Yeah, we have some samples, and we want to make predictions, and what are ways of making this prediction. Yeah, and we have this huge choice of non-parametric, parametric. Do we estimate the right-hand side or the left-hand side? None of you mentioned neural networks, astoundingly, because nowadays the default answer is always, yeah, I use a neural network. Only the question is, which type, with which loss function. But we could use neural network to directly try and estimate the class labels, and we will discuss all these options. Okay. Luckily, Peter paid attention when I made a mistake and told you that we can, I was saying we can integrate the orange curve to find the prior, but that's not true, because this expression is always normalized. Yeah, so if I integrate this over all x, this will always integrate to 1. Yeah, so the prior I cannot extract from this. I need to get separately.